Cool. So welcome, and we are here. We're going to talk about, we've finished Gauss's law, so we've learned so far about electric potential, electric forces, and we've learned about electric fields. And the analogy we used when we were thinking about the analogy we had when we were thinking about mechanics was, you know, the electric force is like the force due to gravity, and the electric field is like little g, which is the gravitational field strength. And what we said was, well, so we had Fe and we had our E. So they're analogous. What we said was, oh, well, you know, you can get from Fg to G, like you can get from Fe to E by saying, well, this is the force per mass, and this is the force per charge. And it kind of seems useful, especially when you go into very different environments. You tend to want maps when you go into different environments. And when we go into different environments, the electric field is very helpful to us. In comparison, we didn't go to many different regions with gravity. We kind of stuck near the surface of the Earth. So it gave us this kind of false idea that little g is the same all over the universe, which is not true. It's a very specific value for living on the surface of this planet. We don't do the same thing with electric fields. We go all over the place. So we're going to mess with E a lot. So it's going to be a very useful thing for us. You might want to think about the next thing mechanically, which is, okay, so I know my weight, and I know the planet I live on, so I know little g. I'd like to somehow link I'd like to get a handle on how much work it takes to climb a mountain and how much work per kilogram it takes to climb a mountain. Yeah. That might be a useful thing to do. We tend to talk about climbing mountains in terms of the height, but in reality, it's how much work we have to do. And that is my weight, that is my mg, times the distance. Yeah? That's the work that's done. And the problem is, I can say that's a 5,000 kilojoule mountain, because for me it is. But maybe for you it's only a 3,000 kilojoule mountain because you have less mass than I have. That makes sense? So talking about how difficult the mountain is in terms of energy is useful, but it depends upon, you know, the mass that's doing the climbing. So getting the joules per kilogram would be a really useful thing to get. And over here we do the same thing with electric fields. It's nice to look at a change in the position in an electric field and say, well, hold on, here I am, here's my electric field. Now, let's remind ourselves, that means the contours are kind of going like that. So the weird thing is we tend to draw the stream paths taken in electricity, whereas in climbing we draw the contour lines. Yeah? When we're climbing mountains, we draw contour lines and we say, look at how many contour lines we're passing. But in electricity and magnetism, we tend to look at electric fields. And they're related, but they're not identical, you know. So here's my electric field lines going across these equipotential lines like we did in lab. And I can say, well, to go from there to there is like climbing a mountain, and that will take so much energy. To go from there to there will take so much energy. But you know what? It might be useful to talk about the joules per coulomb. So this raises us to our next thing, which is electric potential. So in terms of vocabulary, we had electric force, and we had electric field, and now we're going to do is electric potential energy, and we're going to have electric potential. And this was measured in newtons, and this was measured in newtons per coulomb, and this is measured in joules, and this is measured in joules per coulomb. So can you see the pattern that's building up? In both cases, we decide to invent a new term which talks about the something per coulomb, because it's useful. It's not going to be there unless it's useful. And these things, force and potential energy, we got from mechanics. Okay? So that's the game we're going to play. We're going to apply mechanics to electric fields and see what goes on. But with this is one of those things where people get confused. And so I've got a whole bunch of notes at the beginning, and I'm not happy with any of them. But it basically says, you know, I'm trying to kind of get the terminology across and the similarities and the differences. And I've just not found the way that I'm happy with. So I keep taking bites at it from different directions. And I'm going to go through it with you, and hopefully we can make some more sense of it. So gravitational force was the force caused by the proximity of two or more masses, yeah? My proximity to the Earth. Electrostatic force is the force caused by the proximity of two or more charges. And then we have the gravitational field strength, the gravitational force that unit mass would experience, and that's little g. It's not 10 newtons, it's not 10 meters per second squared, it's 10 newtons for every coulomb. And so we have electrostatic force, which is the unit positive charge, the force that a unit positive charge would experience. We've got to be a little bit more careful here, because we only have one type of mass, whereas here we have positive and negative types of charges. So we pick the positive and say we're going to take this based on a positive charges experience. And what we're going to come along with now is, well, gravitational potential energy is the energy stored in a mass by virtue of its position in a gravity field. How much energy does this cell phone have when it sits on top of the box? It has more energy than when it sits on the bottom of the box. So it's by virtue of its position in a gravity field. That's measured in joules. I'm going to talk about the electrostatic potential energy, the energy stored in a charge by virtue of its position in an electrostatic field. And then I'm going to talk about gravitational potential. We never mentioned gravitational potential in Physics 1, or maybe I did, because I knew I was coming here. But the gravitational potential is the potential energy per unit mass. And the electrostatic potential, that is V. That is, when you buy a 9-volt battery, that's what you're buying. How many joules per coulomb does that battery give you? So electrostatic potential is the potential energy per unit charge. So some of these we're very familiar with, and others we've not talked about much. Okay, but it's as simple as this. And my advice is, if you keep coming back to these basic definitions, you won't get lost. If you just head off, you'll get lost in the trees, or at least I did. That's all I can tell you is I did. Whenever you see things that are similar but different, put them down on the same piece of paper. So the story behind this is that I was complaining to my wife that my Physics 2 class was still getting electric force confused with electric field, confused with electric potential, confused with electric potential energy. And she said to me, it's a different class every semester, you know. They're not still getting it wrong. You're still not teaching it right. She's a nice woman. She kind of like tells me the truth. And by chance, I was doing teacher training, a course at USF. So when you teach at USF, they just let you in a classroom. When you teach, that's typical of a university. When you go to a community college, as part of my tenure, I had to do teacher training classes, which is kind of interesting. And one of them was given by a very smart faculty member who I'd worked with before, who was famous for lecturing about not lecturing. He would give you this lecture about how lectures are horrible. And so I had 4 hours every Tuesday night of this thing, and I thought, this is going to be horrendous. And the guy was amazing. He did not lecture. He actually taught in using all these other techniques that he espoused. And although I found it was kind of low-density learning, you kind of couldn't get through much stuff, man, you learned it really well. It's an interesting approach. And we were talking about critical thinking and this desire so people can actually take problems apart and really think about them in depth. And I said, in physics, we always say that we do critical thinking because one of the hallmarks of critical thinking is having a problem, and we solve problems all the time. And then I said, but I don't think that's really critical thinking because, you know, it's just called a problem. We could have called it a question, you know. I think problems, the problems that they mean are not the problems that we mean necessarily. And I said, how can you tell if you're getting critical thinking? And he said, I think if people are comparing and contrasting, they're getting critical thinking. And the light immediately went off with me. And I realized that electric force, electric potential, electric force, electric field, 1 or 2 chapters, electric potential energy, another chapter. People often didn't see them on the same page. So they never compared and contrasted, and I didn't compare and contrast them because I'd already compared and contrasted them. So I started putting them on the same page, and I think there is an improvement. So, and I'm going to do this bit by bit. So basically, we know from Newton's law that the force due to gravity equals big G, big M, little m over r squared times the unit vector. And we have the same thing. It's just instead of masses, we have charges. And instead of, well, displacement, we have displacement. They're similar, yeah. But it's an inverse square relationship in both cases. And we just substitute in mass for charge. And then we have the gravitational field strength, which is the force per unit mass, and the electric field strength is the force per unit charge. Similar. We have gravitational potential energy, which is basically, well, it's the work. It's the work done. You get potential energy by starting off with no energy and doing work. You lift a ball from the floor to the ceiling. You gave it potential energy by doing work. So we have the integral of the force times the displacement. Why is it an integral? Because the force, when you go over large distances, might fall off as you go further and further away from the planet. When you're doing it in a room, it's just F times the displacement. But when you're going through long distances, as the displacement gets further and further away from the planet, the pull of gravity gets less and less. So you've got to integrate. And when you work that out, you get minus G, big M, little m over R. So it's an inverse relationship, not an inverse square. And then when we look over here, what we're going to find is very similar. And then if you want the gravitational potential, which we never talked about, it would be the potential energy over the little mass, so it's minus Gm over R. And we're going to find that electrostatic potential is KEQ over R. So I want to draw, now I just want you to look at this column here. Inverse square, yeah, 1 over R squared. Well, let's draw this out. This is going to be KEQ over R squared R hat. Yeah, I just cancelled it out. I did that, yeah? 1 over R squared. 1 over R, 1 over R. Yep.
So the fourth one, electrostatic potential, that's like a rate.
So the electrostatic potential down at the bottom?
Yeah, that's like a rate. Like in comparison to the potential energy, the electrostatic potential energy isn't a rate, but the electrostatic potential is a rate.
Yeah, because it is the energy per unit charge. Yeah, that's exactly right. Just like the electric field was per unit charge. Yeah, force per unit charge. Good way of thinking about it. So we have inverse squares and inverses, and then notice two charges, one charge. Two charges, one charge. And I believe if you kind of like get comfortable with what's going on that page in broad stroke, you will be able to know the equations. Because if you know this first equation, you can figure out the second equation just by cancelling Q out from it. And if you know the first equation, you can find the you can find the electrostatic potential by recognizing, oh, I've got to multiply by R. So R squared, 1 over R squared goes to 1 over R. And if you know the third equation, you can figure out the fourth equation. So I think it puts it in perspective. This is not my teaching. This is just giving you the preamble, basically. So again, analogies. Gravitational force in newtons, electrostatic force in newtons, newtons per kilogram, newtons per coulomb, joules and joules, joules per kilogram and joules per coulomb, which is the volt. They named the unit. Again, when you name units, it tends to be a bit problematic. So again, and more analogies, I just want to try and wring this thing out as much as I can. So gravitational force is given by that, and the gravitational field strength, and the gravitational potential energy, and the gravitational potential. And then, okay, so we have the electrostatic potential, and the electrostatic potential. Oh, so I'm sorry, no. So now I'm doing this, I'm going down here, I'm going back here, I'm going down here. So, okay. So I'm sorry, no. So now I want to talk about electrostatic potential. So I'm kind of like doing that. So my gravitational potential energy is like my electrostatic potential energy. And you can see the similarity. Ke, big Q, little q over R, G, M over R, yeah? And then we went from here to here. So we have, oh, I'm sorry. I'm messing this up. This slide's got me a little bit off kilter. And then we went from here to here. Electrostatic potential and gravitational potential. And rather than G, we have Ke, and rather than M, we have Q, and rather than R, we have R. But you know, when you learn that UG is equal to MGH, you really cheated. Because it's the change in UG is equal to MGH. Who says that the bottom of the floor is 0 joules? You're really assuming it's 0 joules and then saying, well, the energy to the top of the room is, well, it's really a difference in joules. You know, my delta UG is equal to UG final minus UG initial. And we work this out, and we assume that's 0, so we think that's equal to that. But really, they're not. So it's kind of useful to talk in terms of change in electrostatic potential energy or potential energy difference. And we'll get to that. And we also need to talk about the change in electrostatic potential, and we talk about potential difference. So we'll get to those. Oh man, I'm still going on with this. So this is a bit like, you know, what do I want to emphasize here? I want to emphasize that you get an electric field which is like a topography in a map, and you can choose to pick a point in space, and you can say, what is the electric potential of that point? Or I can take 2 points in space, and I can say, what is the potential difference? Or I can put a charge on here and say, what is the potential energy? Or I can put a charge on here and a charge on here and say, and then I can move the charge, move the charge and say, what is the potential energy difference? So it's really useful to keep asking yourself, am I dealing with a point or am I dealing with a charge in this electric field? Okay. So next, it's really important. Yeah, okay. Next, I'm going to try and codify how you go from one thing to another. So we started off with electric force, and if you take a force and you multiply it by a distance, you get work. Yes, force through a distance is work, and that's the basis for potential energy. So take your electric force and you multiply it by, or you integrate it over a distance, and you get electric potential energy. If I take a potential energy and I multiply it by a charge, I get the electric potential. Joules per coulomb times coulombs gives me joules. Yeah, we had newtons per coulomb times R gives me newtons per coulomb times R distance, which is Newton per coulomb times distance. That is joules over coulombs. Yeah? Divide by Q, newtons per coulomb. Oh, I'm going to go this way. I'm sorry. Divide by R, rather than integrating that, we're going to divide by R. I'm going to take joules over meters, and I'm going to get, I'm sorry, I've got to do some work here. So this is going to be equal to Newton meters per meters, which equals newtons, which is newtons per coulomb. Electric potential is joules per coulomb. Joules per, so we have joules, electric potential, joules per coulomb. I have, man, I'm making a real mess of this. I'm gonna cut while I can, because I'll come back to this next time when I've sorted it out a bit. But basically, this is a map. And if you want to go from electric force to electric field, you divide by Q. If you want to go from electric force to electric potential energy, you integrate over R. If you want to go from electric potential energy to electric potential, you divide by Q. If you want to go from electric field to electric potential, you integrate over R. So this is telling you what to do. If you want to go the other way, you multiply by Q. If you want to go the other way, you differentiate with respect to R. If you want to go the other way, you multiply by Q. If you want to go the other way, you differentiate with respect to R. So when you go from the top to the bottom, you're integrating over R. When you're going from the left to the right, you're dividing by Q. So that kind of gives you another way of looking at the whole thing. And next time, in between time, why don't you look at the units like I was doing, but get them right this time, you know. Don't do what I did and get them all mixed up.
Is that Q divided by 2 or?
Where is that?
Right there.
Oh, this is Q2, the second charge, yeah. And so this is another version of this. I'm sorry. It's just I keep trying to kind of like, you know, smooth it out. But basically it's telling you how to get from force to electric potential. You integrate over R, and if you want to go that way, you differentiate, you know, with respect to R and so on. I'm going to change a bit how this is done. So this is off the fly, but we'll just do it. Let's start off by thinking about a uniform field. There's my mock-up for a uniform field. It's an embankment. I have a certain separation, D, and a certain height difference. That's my gravitational analogy. This is like having a parallel plate capacitor. What that gives me is, well, this is going to be positively charged, so that's going to be at a certain height in the voltage world. And this is going to be negatively charged, so that's going to be a lower height in the voltage world. And there's my slope. Yeah? So let's say, in terms of this mass, I have a mass, and I want to figure out its change in potential energy in going from here to here. You'd say my change in potential energy is equal to m times g times h. And this is mg is the weight times h. Yeah? You simply take the force and you multiply it by the height. So over here, if I have a Q and I want to take it through this delta V, I suppose this should be delta H. Let's call it V, potential difference. Then I would say, oh, my change in electric potential energy is equal to, oh, it's just going to be my, sorry, it's going to be my Q times my E times my V. Oh, I'm sorry, QED. QED. And my E times my D is going to be my V. Okay. I'm going to jump some slides. I'm not doing well at this today. I need to work these notes through again. I'm sorry. I'm going to jump through some slides. I'm going to go to here. So can you find this slide for me? This is of a uniform. Oh, let's go back. No, I'm going to jump these slides. So uniform electric field. So how do I know this field is uniform? I know it's uniform because the lines are parallel to each other. These are electric field lines. These are electric field lines, and they're parallel to each other. They're not parallel in a non-uniform electric field. Yeah? So the streams are diverging. Oh, yeah, there's the mountain top, and here are the contour lines. Yeah? Well, in this case, they're parallel. That means that you're on an embankment. The contour lines are nice and uniform and steady. So we know a separation. What we say is, if the electric field is uniform, previous phrase can be simplified, don't worry about that. Consider a uniform field directed along the minus y-axis, so it's pointing down the page. Consider the potential difference between points A and points B. Because the direction of the electric field is parallel to the displacement, then what we say is, we say my change in potential is equal to minus the integral between A and B of E dot ds, which is minus the integral from A to B of E ds cosine theta, and in this case the cosine theta is 0, cosine theta of 0 is 1, so it goes away, so that goes away. So we end up saying, oh, this is just my change in potential is equal to minus E, the integral between B and A of ds. E is constant, so it becomes minus ED. So for parallel uniform fields, my change in potential is equal to minus ED. The electric field multiplied by the distance. Okay? That's like saying my change in gravitational potential is equal to minus G times D. Gravitational field strength times the distance moved through. electric potential is the joules per coulomb. Supposing I wanted the change in potential energy, what would I do? I would take my electric potential and I'd multiply it by the number of coulombs, which equals minus QED. And up here, that means my change in potential energy is equal to my change in potential times my mass, which equals minus mgd. What does that look like? You know that from physics 1. You didn't call it D though. What does that look like? mgh. So we've been here before, but not in these terms. Okay. So write this in fire. Delta V is equal to minus ED, and delta U is equal to minus QED. Know those, because they're simple. The change in potential energy per unit charge is the force per unit charge times the displacement that the force is moved through. This makes sense. Note that the electric field lines point in the direction of the low potential. The electric field lines are what electric field lines point downhill, and the positive charge is like the boulder. A negative charge would go the opposite direction. Yes?
So in your integral, what does the ds mean? I know ds is...
Oh, I'm sorry. So I've gone and jumbled my slides.
Oh, okay.
ds is the little bit of length. So what it says is, oh, ds would be that, and then that, and then that, and I'm integrating these. But in a uniform field, it's the same value throughout. The ds's are all the same. I'm so sorry, I changed this around just at the, like last semester actually, and I haven't refined my notes. I feel terrible about it actually. When I look at it, it's like, oh, I thought I'd done more on this. So know those two equations. Sorry, I'm having trouble getting my mouse free. It's a bad day today. So change the potential energy of a test charge. Change in potential energy. Not potential, but potential energy of a test charge moved between 2 points. Oh, my change in potential energy equals my charge times my change in potential, which equals QED. So that's where that comes from. So a positive charge loses potential energy when it moves in the direction of the electric field, because it's rolling downhill. An electric field does work on a positive charge when it moves in the direction of the electric field. It gets faster and faster and faster because it's rolling downhill. Its kinetic energy, its potential energy changes to its kinetic energy. So this thing gets more energy, kinetic energy. The positive charge will gain kinetic energy and accelerate in the direction of the electric field. This is just like releasing a mass in a gravitational field. So really try and get these, that boulder is like a positive charge in an electric field. So that being affected by gravity is like a positive charge in an electric field. Really try and build up that familiarity. We're still on the embankment. Because the electric field that points in a negative y direction. Consider the charge that is moved from point A to point B. Now, it's not just down the hill, it's over to the side. So, okay. Does the sideways motion matter? Ask yourself this question. In a frictionless world, does it take any work to keep moving sideways? No. So this sideways motion is free. And that's what we're going to find. So we say, consider a charge that is moved from point A to point B where A and B are not on the same field line. A general form of the potential difference between the 2 points is, well, the difference between the potential at B and the potential at A is change in potential, which equals, and I'll come back to this equation again, I'm sorry, I just pulled it out of thin air because it's introduced in the book using divergent field lines. And I mean, basically I can just turn around and say, oh look, it's going to be the work done, which is basically the electric field multiplied by the distance you move through. And what's the distance you move through? Well, it's if you like, it's E times S. E dotted with S. It is that vector dotted with that vector. And that would be E dotted with S, which equals E times S times the cosine of the angle between them. Yeah? Well, S cosine theta is this guy. So we're back where we started from. We say, oh, it's the same thing, isn't it? It's just minus E times the along the field line distance. That's what we just had. But now we can do things that are an angle. So E dotted with S, okay? And if I want to get the potential energy difference, I just multiply it by Q, okay? Equipotential lines. Now I'm going to go from C to B. And I'm going to find that E is downwards and S is that way, and the angle between them is 90. So there's no work done. So I'm proving what we know from mechanics, we know from physics 1. So let's stop. And let's invent a couple of questions. So remember our two equations. V is equal to minus E times D, and U is equal to QED. Remember that? Yeah. So let's make a couple of questions up. So we can say a uniform electric field points in the plus X direction. Sorry, these should be deltas. What is the electric potential between point A and point B? And I did that because I'm running out of words to describe this. So there's my electric field. Here's my point A. Here's my point B. And let's do something on the diagram. Let's say this is 6 meters, and let's say this equals 7 newtons per coulomb. So I say, well, look, electric potential between, that's electric potential difference, that's delta V, is equal to minus ED, which equals minus, we go in, now here's an important point, you're going from A to B, so am I going uphill or downhill? There's the stream. If I go from A to B, if the point of interest goes from A to B, have I moved uphill or downhill? Moved downhill, haven't I? Yeah? So that means that my potential should be decreasing, yeah? So I expect a negative value here, yeah? So then it'd be E, so that would be 7 times 6 which equals minus 42. What would the units be? Well, it would be newtons per coulomb times meters, which is joules per coulomb, which is volts. So we don't need these guys. It's volts. 42 volts. Let's make it a bit more interesting. Electric field. Let's make it 9 newtons per coulomb. 4 meters. 6 meters. Point A, point B. So now I move from A to B, which is not along a field line. It goes to the side. We did this thing in work, didn't we? When you take something up a ramp, do you take the distance horizontally, do you take the distance vertically, or do you take the distance along the ramp to figure out the work done? Isn't that right? Don't we have the same situation here? Which distance do I say? I say my delta V is equal to minus E times D. So what would that be? It would be minus 9. But what change in position am I going to take? Is it going to be the 4? Is it going to be the 6? Or is it going to be the square root of 4 squared plus 6 squared? So let's have a... Oh, I didn't even get my thing up and going. Now, it's important you look at the direction of the electric field on this. If you think it's 4, put down A. So let's look. So A equals 4 meters. B, you're going to use the 6 meters. And C, you're going to use the square root of 4 squared plus 6 squared. So what do you think? How many people we got? 1, 2, 3, 4, 5. About 20. We've got 17 people. I'm going to stop it. Any more bids? No. Most people saying C. Some people saying A. Some people saying B. Okay. So, here's a ramp. Here's a mass. This is 5 meters. I'll finish in a minute. This is 3, 4, 5. This is 3 meters. This is 4 meters. There's my lifting force, F lift. How much work would be done by my lifting force in going from there to there? Which would you do? You'd say, well, it's equals the work is equal to F times which one of these distances? It's going to be the 4, isn't it? Because it's the force times the displacement in line with the force. Didn't we learn that for work? So you'd say the force times 4. Now, this is the same situation. It's just that which is downhill? That's downhill. That's high, that's low. The diagram is just shifted. Yeah? So now, answer again. Bearing in mind where the top and bottom is. answer again. I'll let this go for a minute, I've got a bit of time. So A if you think 4 on this diagram, B if you think 6, and C if you think this the Pythagorean bit. I'm going to let it go for a few moments and do until 45 seconds. So. Yeah, no, it's the distance in line. So this would be 9 times 4, which would be 36 minus 36 volts. Yeah. If I put 3 coulomb positive charge there, what would my delta U be? My delta U equals Q times delta V, which equals minus QED, which equals minus 3 times 4 times 9. I did that in the wrong order. 9 times 4, let's keep that sacred. So that's going to be 108 minus 108. What would the units be? Delta U is change in potential energy, joules. If I put a minus charge in there, what would the change in energy be in going from A to B? Delta U is equal to Q delta V, which equals minus Q times E times D. I don't want to put that bracket there, which is minus times minus 3 times E is 9 times 4 is D, which equals plus 108 joules. These are not hard. You've done work before, so you've done these, yes.
So when it's electric potential, you're just using the horizontal component, but when it's potential energy, you're going to use the hypotenuse. Is that what you're saying?
No, not at all. I'm saying when it's electric potential, we use that electric field times the distance in line with the electric field. And when it's potential energy difference, I'm using the charge times that. Yeah?
Wait, what does that say? The 3 times, what are those numbers in the red?
In the red.
Yeah.
So that's the charge. That's the electric field. And that's the distance in line with the electric field.
What are the numbers? Is that 399 or
394.
Oh, okay.
Yeah, sorry. Yeah, sorry, that's my bad writing. Yeah? Yeah? Can you stick with me for one more thing? 2 more things. Can you find me the potential difference when I go from A to B? This blue pen's not working for me, but can you figure it out? Let me do some, I can do this 6 times. I'm sorry, I'm going to change one thing. I don't like using the same number twice. Let's make this 7. So the distance is 7, not 6. So there's 3 answers. Hopefully I got this right. So A, B, or C. 36.4, 21, and 19. So how are we doing? Remember, the electric potential is E times D. It's the component of D in line with the E, isn't it? They've got to be in line with each other. I'm going to change coloured pens because that's driving me crazy. Give you maybe another, I'll give you until 1:15. 1:30. Let's have a look. Most people are saying my first choice, which is A, which is relieving to me because that's the one I expected. So let's see why it is that. It's going to be, well, it's going to be minus E times D, which equals minus E times, well, S cosine theta, if you like, if that's S. So equals minus 6 times 7 cosine 30, which equals minus, I forgot the minus signs, but minus 36.4 volts. Yep. And notice, I can write this down as delta V is equal to minus E dotted with S. If I call this the S vector and this the D vector, isn't that what I just did? This is the E vector and this is the S vector, yeah? So, bear with me one more time. E equals 6i plus 2j plus 4k. S equals 1i plus 3j plus 2k. That's in meters. This is in newtons per coulomb. I want to know the potential difference between point A and point B, given that the electric field is 6i plus 2j plus 4k newtons per coulomb, and the displacement vector from point A to point B is 1i plus 3j plus 2k. I want to find out delta V. So I can't figure out the numbers in my head, so I'm going to we'll just do it together, yeah? So delta V is equal to minus E dotted with S, yeah, which equals minus E 6I plus 2J plus 4K dotted with 1I plus 3J plus 2K, which equals minus, can you remember how to do these? 6 times 1 plus 2 times 3 plus 4 times 2. Do you remember that for your dot product? Which equals minus 6 plus 6 plus 8, which equals minus 12, 20 volts. So you can remember that delta V equals E times D, or you can remember that delta V equals minus E times D, man, minus E dotted with D or E dotted with S or whatever you want. And I think that one is the more general one to remember. But, you know, I can get from there to there if need be. But this thing encompasses that. And what can I as a teacher throw at you? I can throw a diagram with distances on it. I can throw a diagram with angles in it. So you have to do component, you have to use trig, or I can throw IJK. Or I could even give you the IJK for this and tell you that this was 6 meters in the positive x direction, just like we did for work, and you'd have to work out what the IJK is for that. Okay? And in all of this, if I ask you for delta U, what are you going to do? By Q. So you don't even need to worry about those equations. Just remember, oh yeah, that's just multiplied by Q. Can you see how it looks complicated, but when you break it down, it's not so bad, yeah? I'm going to pause there.